Hello, welcome to the video lecture for section 3.4 about the chain rule. This is one of these derivative shortcut rules, which is what chapter 3 is all about. But the difference about the chain rule is that it's kind of the hardest one, and it's one you have to use a lot. So it's a pretty important section for just knowing how to do derivatives in general using these shortcuts. So, anyways, here's two problems to try. I'll let you read the first one when you pause it. And for the second one, I'll actually just give you an example here. I'll do number A for you. So what I mean here is here's the function y here. We want to find a function f of x and another function g of x so that this given function here can be written as a composition of f and g. So with A, the way to do that would be to say there's an inner function here, which is the 3x plus 2, and that is being plugged into an outer function, which is the squaring something. So for this example, I would say f of x is x squared, but then instead of actually having x there in this function, we have g of x, which is 3x plus 2. So that way when you do this function composition, f of g of x, the result is this function y we have here. So that's the goal with these other two problems. I'll let you read warm-up number 1, which is a little bit of a weird problem, but try it out. And let's pause it now because the answers will appear in 3, 2, 1. Here's the answer for number 2. So I'll let you check those. This is what I got for part B and part C. I also want to point out there's other possible answers for these. So here's another answer for part C I didn't think of before, which is you could say the f of x could be the square root of x plus 2, and then the g of x that goes with that would just be x squared. And still, when you replace this x with x squared, it works out the same way as if you replace this x with x plus 2 squared. So there's a variety of ways to do it. I should also point out that you could do weird things like just say f of x equals x, and then g of x equals the square root of x squared plus 2, which still technically works, but it's not a very interesting way to decompose that function. Anyways, and for warm-up number 1, I'm not showing you the answer here because I want to work it all out. Because warm-up number 1 is really going to be my explanation for why the chain rule works. So the answer is negative 32 degrees Fahrenheit per hour. If you got that, congratulations. But pay attention anyways to this explanation because it's going to be essentially my proof for why the chain rule works. So to do this problem, let's make up some variables to stand for the different quantities we have. Let's say t is the time in hours. So time is changing like it usually does. Y can stand for the altitude because it's like height, which we're measuring in miles. And let's say that F, it's capital F, we can use for the temperature. Can't use T because we're already using T for time. And the units are just degrees Fahrenheit. So what this question is asking is how fast is your temperature, F, changing as the number of hours increase? Like degrees F per hour, that is a rate of change of this variable F with respect to time. So the question is, we want to know this derivative, the rate of change of the Fahrenheit temperature with respect to time. So like a very small change in the temperature divided by a very small change in time. And what we can do is say, let's make that approximately equal to some actual change divided by an actual change of time. And what I want to do it this way is to figure out what the change in the Fahrenheit temperature would be based on a small change in time. So what you might have been thinking, if you got this one right, is you might be thinking, what happens to the change in Fahrenheit as the time increases by 1 hour, which is a good way to answer this question in just kind of a common sense way. But I want to write that all out with symbols. What is the change in F if the change in the temperature is 1 hour? And if we find that change in temperature divided by change by 1 hour, that's going to be approximately the rate of change at that moment. And we can get this by saying, well, in 1 hour, what is the corresponding change in y, in the altitude? Then let's use the fact that the change in the altitude is approximately, or basically, let's just assume these are all equals here. It'll be simpler. The rate of change of the altitude divided by the change in time multiplied by the actual change in time. So just like before, to find the change in the output of a function, we multiply the slope or the rate of change of it by a change in the input. So this is just like delta y equals m times delta x, like before. And in this case, the dy over dt is, let's write this over here. That's the rate of change of altitude with respect to time, is that 2 miles per hour. And we want to think about units here because it will make a little bit more sense if we think about it that way. So we're doing 2 miles per hour times 1 hour. So of course you just go 2 miles. So yeah, in 1 hour you go 2 miles up. That makes sense. Now what is the corresponding change in the temperature, which is the goal here? That change in the temperature is going to be equal to the rate of change of temperature with respect to altitude multiplied by a change in the altitude. And in this case, that will be the rate of change in temperature with respect to altitude is negative 16. Let me write this way. Negative 16 degrees Fahrenheit per mile. And we're talking about an increase in the altitude of 2 miles. So when you multiply these, the units essentially cancel out, just like the hours canceled out before, and we end up getting negative 16 degrees Fahrenheit times 2, which is equal to negative 32 degrees Fahrenheit. And that's our change in F. What this is saying is that just to overview this logic a little bit, is that if 1 hour goes by, you're going to go up 2 miles, and if you go up 2 miles in that 1 hour, then that's going to be a change of negative 32 degrees Fahrenheit. So it will get 32 degrees colder in 1 hour. So that's basically the answer, is negative 32 degrees Fahrenheit per hour. And the way you can think about that is and this is basically what the chain rule is going to say. It's that if you want to find a change in the output for some change in the input of this function. Well, we have this intermediate function about the altitude. Like, we don't have a function that tells you how the Fahrenheit temperature changes as time goes by. So we need to use this intermediate function, and we use this number 16 here. That number 16 is the rate of change in the Fahrenheit temperature with respect to altitude, and we multiplied that by the number 2 miles per hour. That's your rate of change of the altitude with respect to time. And when you look at this equation, this is basically what we used to get this. We did that negative 16 times 2 here, and it worked out. And you notice that the units of, or the delta y's themselves cancel out, which is kind of what happened when the miles canceled out over here. The y's measured in miles, and that gets canceled out sort of in this fraction. And it turns out that if we get the actual change in temperature, I should say the instantaneous rate of change in temperature, which is what derivatives are all about, it still works. And that's what the chain rule says, that you don't just have to look at some change over 1 hour. You could look at the instantaneous rates of change at any time, and it still works. And so let's look at that. Let's look at the chain rule here. So here it is in all its glory. Let's gaze upon the chain rule for a moment. So we're going to have the same kind of situation as before, where there's a variable x that changes, and as x changes, z changes according to some function g, and as z changes, then that will in turn make y change. So you essentially have a function composition in this situation, because if you replace this z with its version in terms of x, you have a function composition here. And we're going to write the chain rule 2 ways. One in Leibniz notation here, and also the same thing, just rewriting it with regular function notation. So this Leibniz notation looks basically like the situation with the hot air balloon, where the intermediate sort of variable d thing cancels out. Even though, remember, dy over dz isn't a real fraction, it really represents the limit of a fraction as the h approaches 0, but a lot of the times it ends up functioning sort of like a fraction in the sense that these cancel out, sort of, even though they're not really the numerator and denominator of a fraction. They're just this weird parts of weird notation. But the notation is nice because it works as if it was a fraction, and you can sort of pretend it cancels out, and that's a good way to help remember it. Then here is the function notation version. So here, instead of saying dy over dx, we're just going to say we have this function with respect to x that is a composition, and then the instead of dy over dz, that's the derivative of this y function with respect to z. So taking the derivative of this with respect to z is really the same thing as what we have here. And then dz over dx, instead of that, we have g prime of x, and that's just the same thing as taking the derivative of this function here. So dz over dx in Leibniz notation means the same thing as just g prime of x. So you might need to pause it and take a minute to make sure you understand all the different kinds of notation here. But anyways, I'll go on right now to do this example 1. So you can pause it right now and try this on your own if you want. But just because this might be your first time ever seeing the chain rule, I'll just do these problems for you. So starting with A, the first thing we need to do is recognize that this is a function composition. So I'm going to write it like so. The derivative with respect to x. I'm just going to highlight the outer and inner function parts. So it looks to me like the outer part, the f part, is like something to the power 100. The inner part is x squared plus 1. And I'm not going to do this every time, but I'm going to do a lot of extra steps here that we're going to end up skipping pretty soon for this one, just to make sure that we understand what these different notation things mean. So I'm going to write out the f function here. The f of x is, sorry, I should write it as f of z is z to the power 100, and the z itself, we also write that as the g of x function. That's the thing on the inside, which is the x squared plus 1. And we're going to need the derivatives of each of these individual functions here. We need the derivative of the f of z function to get dy over dz, and we need the derivative of the g of x function to get dz over dx. So let's get each of those. Here we're going to use the product, or the power rule, I mean, for f of z. So you get that. And then we can do the same thing with the g function here. The derivative of this is going to be 2x plus 0, or just 2x. And now we can put these together to get the overall derivative. So I'll do that right where we were here, and say this is equal to the dy over dz part, which you could write as 100 times z to the power 99. That's the dy over dz part, times dz over dx, which is just 2x. And this isn't really the answer because the question gave us a function just of x. So we should have a function just of x in it here. So that's what I'm going to do, is replace the z with the x squared plus 1. And write this as 100 times x squared plus 1 to the power 99 times 2x. And that is the answer to the question. We found the derivative of this overall function with respect to x, and we just have x in the answer now. So let's notice the different parts of what we have here. There's the derivative of the outer function ended up just being 100 times that same inner function. This is the g of x that we have right here. So this is our f prime of g of x right here with the power 99 there. And then the derivative of the x squared plus 1 ends up on the outside. Now I might not always do all these steps. I'll probably do it for a couple more of them. And then after a little bit, you want to just kind of skip this and try to do it all like more or less this way, without writing these. You don't necessarily have to write all this extra stuff below here. So let's try B now. So what I want to do to get this one is notice that the outer function is a square root, and the inner function is this polynomial here. So the f function is just the square root of z, and the inner function, the z itself, is a function of x, and that here is the 3x squared plus 5x minus 2. And then we need the derivatives of each of these as well. So the square root is really z to the 1/2, so we could write it that way at first. So the derivative of something to the power 1/2 is just 1/2 times that thing to the power 1/2 minus 1, which becomes negative 1/2. And the derivative of g here is going to be 3 times the derivative of x squared. The derivative of x squared is 2x, so that is 3 times 2x, plus the derivative of 5x is just 5, and then the derivative of 2 is 0, so you just get 6x plus 5. Now, let's plug this all into the chain rule. Sorry, I forgot to write that this is g prime of x here. Anyways, so let's plug this into the chain rule here. We're going to have the derivative of this outer function first. So that's going to be this 1/2 times something all to the power negative 1/2. And just like before, I'm going to skip one little step here. I'm not going to write this in terms of z, because we know we want our answer to be in terms of x in the end anyway. So I'm just going to say the chain rule says f prime of g of x. That g of x should be written in there instead of just writing it as z. So let's write that as 3x squared plus 5x minus 2. And then we're multiplying all of that by the derivative of the inner function, which is the 6x plus 5. This is a little ugly. I'm going to write this again, I think, with the 6x plus 5 in the numerator of it. And then that is divided by, well, there's that 1/2 there from before, and that 2 times the square root of 3x squared plus 5x minus 2. It's the same thing as that. Okay, so that is A and B. Let's do C. Maybe for this one, I'll skip a few more steps. So with this one, I'm just going to write this as the derivative with respect to x of the outer function is e to a power. And then the inner function is x squared. So I'll just write, well, let's write it out. So the inner function is x squared. The derivative of that is 2x. And also, what is the derivative of the outer function? Well, the derivative of an exponential function is just itself. So this should just be f prime of z equals e to the z. So that gives you everything you need. We can now do this derivative. We're going to have the derivative of the outer function. This is like our f prime of g of x part. So it's just going to be e to the power z, but I'll write it as e to the power x squared. So we can have everything in terms of x. And then we need to multiply that by the derivative of the inner function, our 2x part. So it might be easier to read this if you write it as 2x times e to the power x squared. So we have the derivative of e to a power is just e to that same power, but because we're using the chain rule, we need to multiply it by the derivative of the inner function on the outside here. Okay, now let's look at part D. We have e to the x squared. So here, the first thing you need to do is see that, oh, that's the one we just did. I'm sorry. Part D is 1 over x to the fourth plus x squared. So the inner function is x to the fourth plus x squared. The outer function is just 1 over that. So I'm actually going to write 1 divided by something as that thing, x to the fourth plus x squared, all to the power -1. So that's the outer function, is something to the power -1. So I'll write that out here. So what's the derivative of something to the power -1? We'll have to use the power rule here and say that will be -1 times that z to the power -2. So you get -z to the -2. And that's not actually equal to this. I just did a derivative here. All right, and then the g of x function is the x to the fourth plus x squared, and its derivative is 4x cubed plus 2x. So that means we can compute this, the overall derivative we're trying to find is going to be this -z to the -2. So that's the derivative of this outer function you see here is negative something to the power -2, but with the original inner function plugged in. And then that all gets multiplied by the 4x cubed plus 2x. And that's your answer. And you could write it differently if you want as a fraction using the -2 exponent to put that in the denominator of the fraction if you want. But it's not totally necessary. I'm really running out of space. So let's do e down here somewhere. So the thing about e is that it's not just a composition. The e to the x squared part is the composition of two functions that we looked at before. So if that's your, so you say if your f function is e to the z, and you say your z is x squared, or also known as g of x in this notation, then when you do what we have here, if we just have f of g of z, g of x, that would just be the e to the x squared part, but we also have this other x in front of it here, and the chain rule doesn't tell you what to do with the other x, but what does tell you what to do with the other x is the product rule, because this is the product of this function x and this other function e to the x squared here. So at this point, I recommend you pause it and try to do it using the product rule. I'll pause it and do it myself, and the answers will appear in 3, 2, 1. So here it is. I wrote out first just the product rule, writing the original first function. So there's two factors here, two things being multiplied to get this overall function. There's the factor x and the factor e to the x squared. So I have the original x factor, isn't that a TV show or something? The X Factor? I don't remember. Anyways, times the derivative of the second factor plus the derivative of that first factor times the original e to the x squared second factor. So the e to the x squared derivative part, we just did that right over here with part C. The derivative of e to the x squared using the chain rule was 2xe to the x squared. So we did need to use a chain rule just to do that part. But I didn't show those steps here because I just did it. Then the derivative with respect to x of the function x is 1, which, by the way, I think that's really cool. This is one of those nice things about Leibniz notation where this is a thing that would work out if this was actually like a fraction times a number. So like if you did 3 divided by 2 times 3 and then multiplied that by 2, multiplied that fraction by 2, you would just get the number 1. This is like I did it in a different order, but same idea. Like if the d was actually a number 3 and the x was the x variable, we had 2 plugged in, this would just be a fraction. It would cancel out and get 1. But really, this notation doesn't really mean a fraction at all. It means the derivative, which is a limit, the result of a limit, which isn't a fraction. But anyways, it works like a fraction, and you get 1. And I think that's neat. And this is the answer, so that sounds good. Let's move on over this way to try examples 2 and 3. Delete that stuff. So you should try these. These are more of my favorite kinds of problems where you have to do problems 2 different ways. Let me warn you about a couple things. First of all, I think example 3 is actually a lot easier than example 2, so maybe do example 3 first so you don't get frustrated with example 2. And example 2b is hard. And I just realized I wrote ax instead of as, and I also should have said use the chain rule and the product rule. So my big hint here is that this is a product of 2 functions, and you need to use the product rule first before you use the chain rule. So just correcting myself there. So yeah, let's do these now. Pause the video because I'll pause it too, and the answers will appear in 3, 2, 1. So here they are, and just like I suggested, you do number 3 first. I'm going to show you number 3 first here, and then we'll scroll over to see number 2 on the right in a moment. So first, I used the product rule. The first factor function was e to the t. The second one is also e to the t. And this was kind of fun because the derivative of e to the t is just e to the t. So here's the derivative of the orange e to the t one, and here's the derivative of the green e to the t one, but it's all the same thing. So you just end up with e to the 2t plus e to the 2t when you do t plus t to combine the exponents, and that is the same as 2e to the 2t. So that works. And for b, the trick is that, this is basically just the chain rule. There's the outer function, e to a power, so the derivative of e to that power is just e to that power, and just leaving the original 2t plugged in, and then multiplying that by the derivative of that 2t, which is just 2. So this looks kind of weird. Sometimes people get confused what the relationship between the two is. It kind of looks like -2, or it looks like it might be in the exponent sometimes. So it's just nicer to write it on the left, but not a big deal. Anyways, example 2 is harder. First, this is a kind of standard quotient rule problem, which isn't too bad. I just did the low d high, that's low d high minus high d low over the square of what's below. And it worked out without too much trouble. This was a lot of work with the product and chain rule combination. Now, because you can write that denominator as x squared plus 1 to the power negative 1, it turns into a product like this. And here's my first step with the product rule. I just did the original first factor, x, times the derivative of the second factor, which is a lot of work here, and then plus the original derivative of the x factor, which is the derivative of x with respect to x is just 1, and then the original second factor. So then here's the work I did to do this problem, which itself requires the chain rule. So I did it on the side down here, and the outer function is something to the power negative 1. The inner function with this chain rule problem is x squared plus 1. Then the derivative of that outer function becomes the exponent comes down, and then you subtract 1 from it, with the original inner function plugged in, and then times the derivative of the inner function there. And then I just wrote that power negative 2 as the denominator of the fraction and plugged it back in. So here's, I just went from this step to this step by plugging things in. And then I have this fraction plus this other fraction. To be able to combine them into a single fraction, I multiplied both sides by x squared plus 1 over here to make them both have that same denominator. And then they can be combined like so to get the negative 2x squared plus x squared becomes negative x squared, and then there's a plus 1 in there with that combined denominator. And give yourself a big pat on the back if you got that, because this worked out. We got the same answer using the chain rule and the product rule together as we got using the quotient rule. And also give, yeah, here's a gold star for you if you got through all of that. That is an excellent amount of determination you just showed, and calculus skills as well. So let's go on to the next one. This is also a really mean one. So I'm wondering if I should do this. I'll pause it to do this one. You should give it a shot, but don't be afraid if you get stuck and you have to watch my answer. But either way, write down the right answer at the end, one way or another. So let's try it now. I'll pause it to write down the right answer in 3, 2, 1. Here's the answer. If you got this, again, give yourself a gold star because it's tricky. Especially if this is your first time taking calculus. The chain rule is something that you'll get good at if you practice it enough. But it does take a lot of practice, and it is weird at first. So this is an example of a really hard problem if you've never seen it before. Anyways, you need to use the chain rule twice here. So the first time I used the chain rule was when I recognized this inner thing here as the square root as the power 1/2, and this has a function composition. So there's the outer function, which is just to the power 1/2, and the inner function is this other messy thing there. Now the inner function here, the outer function, when you take the derivative of that, you get the power 1/2 there, and then 1/2 minus 1 becomes negative 1/2 with the original inner function still plugged in. And then the chain rule says multiply that by the derivative of the inner function. Now the inner function itself is also a composition because there's the 2 to a power. That's like the outer function is 1 plus 2 to a power. And then the power itself, 3 plus x squared, is the inner function. So to go from here to here, we're using the chain rule a second time. And let's see, there's the oh yeah, so the derivative of 1 is 0. The derivative of 2 to a power is natural log of 2 times 2 to that same power, just leaving the original function plugged in there, and then multiplied by the derivative of that original inner function. So that's using the chain rule a second time. And then just doing the derivative of 3 plus x squared gives you 0 plus 2x. Oh, I need to erase my gold star because I made a mistake. This should be 2x in there, not x squared. So, oh well. If you got it, congratulations. Now, let's see. We can actually write this in kind of a better way by canceling out this times 2 and this 1/2 here. So maybe that would be better. And maybe let's write this negative 1/2 power as the square root in the bottom of a fraction. Just to make things look nicer, we can call this whole thing x times the natural log of 2 times 2 to the 3 plus x squared. That's everything from the top, and then the bottom will have the square root of 1 plus 2 to the power 3 plus x squared. What a mess. Anyways, that is a difficult problem. Now I got it right after checking my answer. So yeah, I like to think of this as peeling away the layers of an onion. We have an outer layer, which represents the square root function, and then this inner layer, sort of medium inner layer, which kind of represents the 1 plus this 2 to a power function. And then the inner layer is the power 3x plus squared itself. And it doesn't look quite like an onion. Maybe it looks like a jawbreaker candy. That's the idea. You peel away the layers and you get to the middle eventually, and that last thing you do, if you do it right, is taking the derivative of that inner layer. So here's some practice problems to do. This first one is pretty similar to that warm-up problem. I'll give you a hint. The units for your answer, if it's asking how fast, like the term fast generally, or slow generally, is talking about time. And it's asking how fast is the length of the bridge increasing, and we're measuring length in these micrometers. So the units for your answer will be micrometers per hour. Are we talking about hours? Yeah. So micrometers per hour is how fast the length is changing. So anyways, I'll let you try these problems, and let's pause it now because the answers will appear in 3, 2, 1. And here are those answers. So the first one, we're just multiplying the two rates of change involved in this function composition. So the micrometers per degree Celsius times the degree Celsius per hour rate of change gives you a overall speed, or how fast kind of thing, of 0.6 micrometers per hour, which is not a good speed to win a race, but it might be important if your bridge is getting bigger at that rate. You don't want your bridge to fall down because it doesn't fit anymore. Anyways, let's look at problem 2. So with this one, the inner function is x plus 2. The outer function is pi to a power. So the derivative of that outer function, pi to a power, you just get natural log of pi times pi to that same power. But the chain rule says we need to multiply this by the derivative of x plus 2 on the outside. And the derivative of x plus 2 is just 1, because the derivative of x is 1 and the derivative of 2 is 0. So it simplifies like so. And with the second one, the first thing to do, oh, I did this using the chain rule, but you could also do this using the quotient rule. You should get the same result, hopefully. But yeah, using the chain rule, I just wrote it as e to the z plus 1 to the power -2, and the -2 gets brought down. That's the derivative of the outer function, and the exponent becomes -3 in the outer function. We leave the original inner function plugged in there into that derivative, and multiply that by the derivative of the inner function. And that derivative of e to the z just becomes this e to the z over here, plus 0. So I just wrote it in a slightly different way here, and it simplifies to that. So excellent work. If you did all of these, we'll practice it some more in class with some tricky kinds of examples too. And of course, you should get help in class if you're struggling with these. And I will see you then.